Okay, we're going to introduce a new concept now, and that is of entropy, which is usually given the symbol S, and it is usually described simply as the degree of disorder of a substance. Apparently, that's not, a lot of people have issues with that, and it's probably better to think of it as thinking here as it's the sum of all the possible arrangements a substance could have, of all the energy in that substance, how the particles and the particles as well. So for example, if you've got a block of ice at -5 degrees C, there are a certain number of quanta of energy in there, and they could be distributed evenly through the ice, or they could be grouped in one part of it. And entropy is the sum of all the possible arrangements that they could exist in. So probability is you have to understand probability really to understand what entropy is. Okay, so anyway, we won't worry too much about that, but let's have a think about here's some values of entropy. By the way, before we say anything, if you look at the units there, joules per mole per Kelvin, you probably remember the units of specific heat capacity. Specific heat capacity are joules per gram per Kelvin. And of course, grams will just, you could change that for mole, the molar heat capacity. So that should give you some kind of insight of what entropy actually is and why it's got those units. Okay, so won't worry too much about that, but let's think about, let's look at diamond and graphite here. Well, first of all, they've both got very low entropys, haven't they? 2.4, 5.7, much lower than anything else. And that's a reflection of the fact that they are highly ordered crystalline structures. Diamond has got, I think if you look in a data book, it's one of the lowest entropies, 2.4 joules, and that's even lower than graphite. If you think about graphite, there is slightly more disorder in graphite than in diamond. There's more possibilities. Diamond, obviously every atom is covalently bonded to 4 others. Graphite is only to 3, and you've got the delocalized electron, which can, obviously that is going to be another possibility for lots of different arrangements. Where are the delocalized electrons? They can be in different places. So that's why graphite is slightly higher. Okay. Oh yes, I should also say this, this sign, which we are familiar with. That's the standard entropy. So that's at 298 Kelvin. See, if you increase the temperature, you're going to give the molecules, atoms, more energy. There's more different ways in which that energy can be distributed, so the entropy is going to go up. Or the other way of thinking of disorder is, if you increase the temperature, the particles in a gas are going to move around more, so you're less certain of where they're going to be at one particular time. They're more disordered. Okay, so moving on to iron, metal. Okay, so fairly highly ordered, metallic lattice. So that's pretty low. Sulfur. This really is referring to this is per sulfur mole of sulfur atoms, but it's actually S8. So that's a reasonably ordered structure. The S8 molecules all held together by van der Waals forces in a crystalline manner. That's quite low. Magnesium oxide and sodium chloride and magnesium chloride, these are all ionic solids, aren't they? So they're, not surprising, they're all quite on the low side. Magnesium oxide is the lowest. I think magnesium chloride is higher than certainly than sodium chloride, probably because there are 2 chloride ions per every magnesium. So there's more atoms in, there's more ions in a mole of magnesium chloride than there is in sodium chloride, so there's more possibilities for arrangement, different arrangements of energy and particles, and so there's more entropy. Let's have a look at the alkanes then. So you can see there, as we go down, the alkanes, as they get bigger, the entropy gets bigger. And that's not surprising because you've got more atoms in each molecule. There are more possibilities of where the atoms are arranged with respect to each other. And you've got more atoms as well in 1 mole of C3H8 than you have in CH4. Then if you have a look at water, and I'm not entirely sure how this works out because you can't, this is 298 Kelvin really, isn't it? But you do see it in data books. Standard entropy of liquid water, 69.9, and water as a gas, steam, you obviously can't exist steam really at 298 Kelvin, and the standard atmospheric pressure, can it? But anyway, it's quoted as that. It's a lot higher, as you'd expect it to be. So hopefully you've got some feeling of what entropy is there. Just think of it as a disorder. As I say, some people will take exception to that. Okay, now what we are interested in as chemists very often is we're interested not in entropy, but we're interested in entropy changes. Okay, so we're going to use this entropy changes in chemical reactions, just as we have looked at, you know, enthalpy, changes in enthalpy, delta H. And we're very often, we're interested in the entropy change. So we're just going to quickly show you, so I want to show you how to work out the entropy change of a chemical reaction, and it is given standard entropy values, and it's very straightforward. I'll just give you a couple of examples. Okay, so right, let's think of the reaction. Right, what you might get in cracking. So let's say you get some decane. Decane is C10H22, and you're going to crack that. Okay, so this is a you're going to crack it. I will put the state symbols in, and you're going to turn it into 4 molecules of ethene and 1 molecule of ethane. Okay, we've got to work out delta S for that. So we're given S values in joules per mole per Kelvin, standard ones. Okay, so for C2H4, I'll write them down in red here, so let me write it down, but the value for C2H4 is 219.5. C2H6 is slightly higher because there's more atoms in it, 229.5. And for decane, it's going to be quite a lot more. It's 425.9. And that's even though decane is a liquid, and these are obviously these are gases. Okay, so what we have to do is delta S is equal to sum of the S of the products minus sum of the entropy of the reactants. Okay, so how do we work out that? Well, this value, we've got to times that by 4, and then we've got to add it to that one, and that comes out to be 681 point, can't possibly be right, can it? No, it's not. 1,107, yeah, sorry. $1,107.5. So that is 4 times 219.5 plus 229.5 gives you that. And here, well, this is just there's only one reactant, which makes things easy. It's 429.5. So in this case, delta S is going to be equal to 1107.5 minus 425.9, which is equal to, and I'm going to put the plus sign in there, just like you quite often do with delta H. Even if it's plus, you put it in just to emphasize it, so you don't think it's negative. 681.6. So we can see that there is a entropy. So delta S is positive, so entropy actually increases there. So the entropy is increasing, and we'd expect that, wouldn't we? Because we're starting off, and I should have put the state symbols in for the that's yeah. We're starting off with 1 mole of one molecule, and we're breaking it up into five smaller molecules. So it's obviously going to be more disordered. So that, you know, we've increased the number of gas moles, is another way I should say. Yeah. So that's definitely going to be, you would definitely expect that to be an increase in entropy. And if you worked it out and it wasn't, then you obviously realize you've done something wrong. Okay, let's look at one more example there. Let's have a look at magnesium. Magnesium solid. Get a piece of magnesium ribbon, burn it in oxygen, and that is going to go to magnesium oxide. Now, before we work it out, what would we expect? Entropy positive or negative value for delta S? What do you think? Well, hopefully, I'll put that in there. It should be fairly obvious that you would expect delta S to be negative, because you are forming 1 mole of a highly ordered magnesium oxide from a solid, but from a gas. So there's no gas anymore. So that is obviously going to decrease the entropy. So there's a negative entropy change there. All right, so let's put the values in. The delta, so the S values, I'll do them in red here for this. If you look at the data book, joule per mole per Kelvin. Right, for magnesium, it's pretty low. It's 32.7 because it's a solid. Oxygen, now this is quoted per molecule of oxygen. So this is for each, this is per, sorry, not per molecule of oxygen, this is per atom of oxygen in the molecule. So the value there is 102.5. So for O2 itself, it would be 205 would be the value there. Magnesium oxide, right, that's going to be pretty low because it's a highly ordered ionic solid, 26.9. So what is delta S for this reaction going to be equal to? Delta S is going to be equal to 26.9 minus, right, let's add those two together, 32.7, 102.5 gives us 150. Gives us 135.2. So that's going to be minus 135.2. Which is equal to minus 108.3. So yes, our entropy, our delta S value for that reaction is negative, yeah, because we are getting rid of a gas, really, turning it into a solid. Okay, so working out entropy changes of reaction is pretty easy. We'll leave that video there and we'll talk about the importance of entropy in the next one.